So good morning, everyone. It is my pleasure to introduce the keynote speaker of today, Dominik Janzing. So at the beginning of his research career, Dominik worked on topics in quantum information theory, quantum thermodynamics, quantum complexity theory, and at some point he also became interested in causality. And I think that's a topic or a part of his research that most of us will be more familiar with. So over the years, Dominik has made many contributions to the field of causal inference, and he has co-authored a textbook, Elements of Causal Inference. And one aspect of his research that I really admire personally is that it often shows very creative and original ideas, often also conceptual, new ways of thinking about things. And well, perhaps we will even see a bit of that in his presentation today. So without further ado, here's Dominik Janzing.
Thanks, Joris, for the introduction and for inviting me. I really enjoy speaking at UAI because I like UAI. It's a nice conference. Yeah, so all DAGs are wrong, but some are useful. Let me start with a personal remark. I started my career in causality with causal discovery about 20 years ago. And it still fascinates me, but whenever I try to apply it to real problems, I was unhappy. Not only that the results are often wrong, even worse, we rarely know whether they are wrong. And even worse, we rarely understand what wrong means. And I decided this is not the way the show can go on. So we called it came from a long time in academia. I worked with Amazon since 6 years. So industrial research also gave me a different perspective on the academic bubble. In publications, causal graphs are everywhere. You find quite complex ones. This is just a random choice. Article on COVID. You find them in medicine, climate research, economy, business, brain research. So it seems that they are more and more accepted in different communities. However, there are quite skeptical views from important people. So this is Guido Imbens, Nobel Prize in Economics, 2021, on causality. He says in a very interesting article, the DAG literature has not shown much evidence of the alleged benefits for empirical practice in settings that resonate with economics, with economists. Yeah, okay, so we should take that serious. Rephrasing his idea in my words, how makes sense to me. He's saying that causal relations in real life are in fact complex. This is what he admits. But the parts we know, or the relevant ones, often reduce to something simple. And you know, all these simple structures that in scenarios like the potential outcome frameworks. So after all, in most applications are about estimating the effect of a treatment on a target in the presence of covariates with potentially an instrumental variable in the lucky case. Okay. Further criticism that you also find in this article and that I agree with, definitely. Interventions impossible for most of the nodes if you have complex stacks. But even worse, and this is was part of my first slide, interventions are often ill-defined because variables are aggregated and the effects depend on the implementation of the intervention. And often it's unclear what qualifies an action as an intervention on a certain variable. We've written a paper on that. that discusses that from a slightly philosophical perspective, but with a lot of toy problems, called phenomenological account for causality in terms of elementary actions. But first, I would like to ask you, why do you want to infer the causal DAG in the first place? In case you care about causal discovery, ask yourself why. In case your friends care about causal discovery, did you ever ask them why? So I'll give you 15 seconds to think about that. My clock is not very precise. Trying to infer whether you are thinking. Okay, but let me give you my answer. I want to understand processes by analyzing its components, their components, and find the problem if they don't work. It's also the idea of root cause analysis. This is an old phone, and maybe you also enjoy how it looks from the interior. This is one of the machines I spent my late childhood with. They were not in use any longer, but just because they were nice. Okay, so this modular perspective aligns with the modular perspective in graphical models. So one think of the mechanisms as formalized by the conditional distribution of each node given its parents. So this is, here. The joint distribution factorizes accordingly, or in terms of structural causal models, where you have independent structural equations on every node. Okay, with independent noise variables. And a highly simplified example, the Amazon supply chain with different mechanisms like simulation, a bidding mechanism, a forecast, planning, and inventory. And then the joint distribution factorizes accordingly. And so each term in this factorization stands for a mechanism. So that's a context where you can really think that a big company, this really corresponds to different teams, to different software. So the modular perspective is quite intuitive, well justified. The key phases of this talk are, first, that causal DAGs can help solving tasks. Oh, thanks. Oh yes, that's reliable situation. Yes, it switches to. Thanks. Okay, causal DAGs can help solving tasks that have no obvious reduction to computing a treatment effect and rely on a causal model with multiple variables from the outset. And second, using DAGs for these tasks shows us whether the DAGs make sense, even when interventions are ill-defined for most of the variables. And just as an example, I will present 3 tasks. Explain distribution change. So let's say you observe week-over-week changes in the statistics of the supply chain. That's something important in companies compared to last week. So you observe that the joint distribution changes, and according the sparse mechanism shift hypothesis, which has been phrased, for instance, by Schölkopf and collaborators in Toward causal representation learning, try to explain them by changes of only a few mechanisms. So here in this example, we explain the change of the joint distribution by the change of one conditional distribution, which is one mechanism. And then we want to quantify the contribution of each mechanism if there were several changes observed. Of course, there's a limitation of the sparse mechanism shift hypothesis. The short answer is whether we should believe in it. No, it's just a working hypothesis. It's kind of razor inductive bias. Try to find a simple explanation as possible. The long answer is simultaneous change of many mechanisms may indicate that the model missed a common cause. For instance, in this toy example, your hypothetical DAG is that one, and then you observe the week over week changes where all the conditional changed. It could be that you missed a common cause X0 whose distribution changed. And so in the true DAG, in the right factorization, only that mechanism changed. And here you observe all these three changes. So the strongest support for the causal DAG in absence of interventions would be observe that all other mechanisms remained the same. At least it's a strong support. This distribution change is part of the open source library DoY. We have also a JMLR article that describes these contributions that we made to DoY. The second task, it's quite related, root cause analysis of outliers. And we have studied that in an example of cloud computing. So I work for AWS, Amazon Web Services. So in cloud computing, you may have a service or an application that consists of many dependent microservices, which call each other. So in this case, I think it's 37 or 36. And the causal structure is roughly known. So when service A calls B, then the latencies propagate from B to A. So in a way, you have an approximate causal DAG according to the dependencies of the service. It has to be taken with a grain of salt, but nevertheless, my colleagues did root cause analysis on this graph. So this is an application that's a virtual pet shop. It's just a simulation of a pet shop, but you can really use it and study the data, and the data set is open source. And they showed how to perform root cause analysis with artificially injected incidents at different nodes, and then using this approximate DAG to find the root causes. And it worked. In a little bit more schematic description, this is the following. So how to use the DAG for root cause analysis of outliers. So you just have some kind of anomaly detector that tells you whether the value is normal or extreme at certain nodes. And then you can sometimes trace it back to a unique root cause in the lucky case. So here X3 is probably the root cause. One may argue that this DAG is only true in the normal mode. It doesn't hold any longer if there are extreme values. I mean, that's a valid point. In every single case, you may argue like that. But the more often we rely on these excuses, the more we have to ask ourselves where the DAG stands for in the first place. So this is, for instance, a test of plausibility. When you are given a certain pattern of anomalies, or here's an anomaly, and here's an anomaly, and here's one. Here, the propagation of anomalies seems to be somehow unrelated to the DAG. So the DAG suggests three independent root causes whose actual root cause may be an unobserved variable. So that's not really supportive of the DAG, this pattern. Here also a schematic picture of branching. So here you have an anomaly that splits into two different branches, and here you have again two different branches. So this branching into two cascades is quite plausible, but the causally reversed process would have three independent root causes. So if you reverse all the errors. So in this sense, the pattern of anomalies tells you something about the directions of the errors as well. So the strongest support for the DAG is that all outliers can be traced back to a single root cause. This branching is also mentioned in The Direction of Time, an interesting book from the 50s. Okay, but there's another aspect. We want to validate causal directions also by the strength of anomalies. Namely, there is a certain sense in which weak anomalies cannot cause strong ones. And the idea, okay, so to formalize this idea, I have to introduce our anomaly score. It's just basically a minus logarithmic tail probability for some feature map that describes the interesting aspects of the outliers. So for instance, this is just a one-sided quantile, the minus log of a one-sided quantile. And this is two-sided. And so by quantifying anomaly just according to the probability, we have some interesting properties of anomaly scores. First, we have this probabilistic calibration, which tells you that anomalies of strength S occur with probability e to the power of minus S at most. Then we have the flexibility. It applies to every domain, whether categorical or multivariate whatsoever. Scale independence. You can compare anomalies across different units. And it's related to statistical testing. So S can be seen as test statistics, then e to the power of minus S of x is a p-value for the hypothesis x has been drawn from p of x. So just for the single value, it provides you the p-value. And then here is the idea why weak outliers cannot cause strong ones in a certain sense. Just because rare events cannot explain extremely rare events in the following sense. If event A happens with probability 1 over 100, but B only with probability 1 over 1,000, then A is not a good explanation of B, because in 9 out of 10 cases, A happens without B. Hence, we want to know what else happened in addition that made P likely. And from just using the Bayesian formula, we know that conditioning on an event can only increase the probability significantly if the event is extremely unlikely, for obvious reasons of the Bayesian formula, which is, so this quotient is still small in this case. So the comparison of outlier scores can tell us the causal direction. To make this a bit more explicit, we also need this independent mechanism perspective. Let's have a toy example with the causal DAG x causes y, and given the outlier observations xy. The hypothesis 1 is mechanism P of x worked as usual. That is, x has been drawn from P of x. This can be rejected at p-value e to the power of minus S of x by construction of the anomaly scores. The hypothesis 2 reads mechanism P of y given x worked as usual. That is, y has been drawn from P of y given x equal to x. And we can show that this can be rejected at p-value e to the power of the difference of the anomaly scores, subject to some kind of monotonicity assumption that we needed. So when the difference is large, then also mechanism 2 doesn't work as expected, didn't work as expected. So if we have the following observation that there are two strong outliers, but y is the even stronger one, then, and we ask ourselves what is more plausible, x causes y or y causes x. And direction x causes y is implausible because neither p of x nor p of y given x worked as expected. But direction y causing x is plausible because the mechanism p of y was corrupted probably, but p of x given y may have worked as usual. So the outlier x is explained as a downstream effect of the stronger outlier y. Okay, so these were two quite related tasks. By the way, do you still hear me when I'm speaking here? It's a bit, okay, I will do my best, thanks. The third one, which is sort of central to this talk, merge probability distributions. So the toy example is infer the joint distribution of x, y, z from the joint distribution of x, y and the joint distribution of y, z. So it's easy to see that in general, this is rather ambiguous. And I want to make this ambiguity quite explicit. So take any structural equation model for P of x given y and P of z given y. So here y is modeled as a common cause, just not because it needs to be the cause, it's just because it's easy to get an intuitive sense of the ambiguity. Then you can show that the ambiguity consists of the dependencies between this noise term and this noise term, because these dependencies don't affect this marginal distribution and don't affect this marginal distribution. So the ambiguity of choosing the dependencies here correspond to the ambiguity of the joint distribution given these two marginal distributions. However, the key thesis is that, okay, this slide corresponds to the explanation I just gave. So here is a potential confounder that creates the dependencies between x and z. Okay, the question is this merging unique if you have causal information? And here you have this causal statement, x causes y without confounding with the corresponding causal DAG, and y causes z without confounding with that DAG. And we want to merge them. So we screw the DAGs together here. And we conclude the following. A direct link or a confounder between x and z would render y and z confounded. So therefore, we have conditional independence corresponding to this DAG, x independent z given y. So the joint distribution can be constructed using this conditional independence. Do we believe this? So, do we trust this construction? So the academic optimist feels quite safe, but when I built that, the DAG broke due to its own weight. And actually the goal was to show that it only breaks if I put more and more stuff on it. But then it turned out that it just broke from its own weight, and I thought the metaphor is even nicer, because what I'm presenting now is basically how DAGs break from their own weight by merging them together. So first, just to be a bit more precise, we have to explain why this conclusion was hand-wavy. So one can show that with a confounder that affects all three noise variables in a non-generic way. I don't want to go to the details because it's getting convoluted. Then you can show that the interventional probability of y do x is still the same as the observational probability y given x, so there's no active confounding here. And likewise, the interventional probability of z given y is the same as the observational probability, so there's no active confounding here. Yet there is some kind of convoluted joint confounding that ensures that the conditional independence that we use for the construction breaks down. So for this kind of non-generic tuning of confounding paths, the construction fails. So to get the merging operation safe, we require additional assumptions like genericity of confounders, so confounding paths between x and z also affect the interventional probability of z to y, for instance. Or you get safe merging via the assumptions of causal discovery algorithms. So when you think about it for a while, it turns more and more out that assumptions that enable causal discovery also enable merging probability distributions to some extent. So these tasks are somehow related. And this is something that I want to understand more deeply. You have the model class of acyclic linear non-Gaussian additive noise models like Lingam with confounding. So here you have just the usual Lingam model. But here you have shared noise variables. So this epsilon describes the sharing. And here you have independent noise variables as usual. And then we have shown that if the joint distribution is assumed from the above model class and x causes y and y causes x, both unconfounded according to this model class, then you can show conditional independence, so you can uniquely merge the probability distributions. So if you believe in this model class, then you can uniquely reconstruct the joint distribution from the marginal distributions. Why is merging an interesting task? And you will see that we don't want to do it for the sake of merging, actually. It's just for the sake of testing causal models. So it yields a method for falsification of causal for causal models without ground truth. So you think of the following scenario. For instance, in this linear non-Gaussian case, you decide whether a model class fits the marginal distributions reasonably well. And this is, of course, always a difficult decision because it never fits perfectly. So you decide, okay, this is reasonable. The dependencies, for instance, for the linear additive noise model, you perform some kind of dependence test and then, okay, yeah, the p-value is not too tiny, so I accept the independence of noise. But in this step, you are not supposed to look at the joint distribution yet. but then you predict the joint distribution and check, was the prediction better than predictions without the causal model or with a different one? So whether your causal inductive bias enabled better merging than without that causal bias. And of course, it doesn't prove that the causal assumptions are right and that the causal models are wrong, that the causal models are really causal. But following Karl Popper's theory of science, the strongest evidence in favor of a hypothesis comes from constructing falsifiable predictions. And the more options you have for falsification and you test them and the model class or the model is not falsified, this is the strongest support you can get. Okay, but merging is only an extreme example. In a way, causal discovery algorithms always predict properties of joint distributions implicitly in the following sense. You're given a set of variables, x1 to xn, then you apply the algorithm to overlapping subsets of variables. And then you assume that the output graphs Gn to Gk on these subsets are compatible in a sense that will be defined later here in talk. Then there's the implicit prediction. The joint distribution of all the nodes is such that A's output G, which is also a graph, is compatible with the subgraphs on the subsets. So whenever you think that a causal discovery algorithm should come with the implicit promise of not contradicting itself when you apply it to a larger set, then it implicitly predicts properties of the joint distribution. So it doesn't necessarily allow you to really merge the distribution in the sense of getting a unique joint distribution, but at least you predict some properties of joint distribution. And this is exactly the causal versus the probabilistic marginal problem. So given marginal distributions on subset of variables, then the probabilistic extensions would just be the convex space of distributions on all the variables with the above marginal distribution. So it's easy to see that this is a convex space. The problem is called causal marginal problem, probabilistic marginal problem. I think also, yeah, just probabilistic marginal problem. But the causal extensions relative to an algorithm A are as follows. These are the set of distributions for which A infers a joint causal graph G that is compatible with the subgraphs inferred by A from the above marginals. And in the good case, we have a strong test for the algorithm if the causal extensions are a small subset of the possible probabilistic extensions. Then we have a strong test for our inductive bias. So the causal extensions are far from being convex, as far as I know. I think it's a quite convoluted set. Here we have a weak test, so it's almost indistinguishable. So that's useless for our purpose. So what we are suggesting is benchmarking causal discovery via self-compatibility. And this is just a toy example. So let's say this is the joint DAG with 4 nodes. And then we apply an algorithm to these 3 variables and to these 3 variables and get these 2 outputs. Then you see that they disagree with respect to the edge x causes y versus y causing x in E. So A contradicts itself regarding the direction. And if you ever played around with causal discovery algorithms, then you see it happens all the time. But the big question is compatibility benchmarking easy to gain? Is it really a strong condition to not contradict itself? And in order to find that out, we have the following challenge: invent nonsense algorithms that are compatible when applied to different subsets of variables. And in addition, that the output satisfies the Markov condition. Otherwise, we have the trivial solution of inferring no edges at all. And there's a nice proposal that I heard from a colleague when we first suggested that. Just use alphabetic ordering. So infer xi causes xj whenever the variable name of xi occurs before xj, according to alphabetic ordering. It's obviously nonsense, but doesn't contradict itself, does it? So I will come to this question later. I modified this proposal into entropy ordering. Infer xi causes xj whenever the Shannon entropy of xi is smaller than the Shannon entropy of xj. This is motivated by proposals that I heard again and again back then in 20 to 15 years ago when we studied this cause-effect pairs, that people just suggest, okay, but the second law of thermodynamics tells you that entropy is always increasing, therefore the effect has more entropy than the cause. I think this is completely nonsense, and I discussed that in a paper, The Cause-Effect Problem, Motivation, Ideas, and Popular Misconceptions, where I'm arguing that this is a misinterpretation of what the thermodynamic error of time says. But nevertheless, it's a proposal that is not as obviously nonsense as the first one. So we want to look into that. So does node ordering yield compatible results? So here's the, let's say we have x2, x3. Let's say they are already ordered. Then we draw an arrow, x2 causes x3. And the output, and the output for x1, x2, x3 reads x1 causes x2, x2 causes x3, and x1 causes x3. Okay, so are these two DAGs consistent or not? So from a superficial perspective, could say, okay, but this error is uncommon, yeah, and there's just this additional confounder. But, there's, this slide was what I wanted to show. So the DAGs agree with respect to the existence and direction of the link x2, x3, but they disagree with respect to intervention probabilities for generic joint distributions. Because here, P of x3 do x2 is just the observational probability. And here you have vector adjustment. This is the vector adjustment formula to compute the interventional probability. So, and those two generically disagree. Okay, so it depends on your notion of compatibility, whether this is an agreement, and we strongly argue in favor of compatibility notions with respect to which they don't agree, because otherwise it's easy to deal with. So to formalize that, first we defined graphical compatibility. So we have graphs with nodes S1 to Sk. And the graphs are called graphically compatible if there is a graph whose nodes are supersets of all of them and whose marginalization to the subsets coincides with Gj. This requires a class of graphs that admit marginalization. So people from causal discovery know that this is not possible within the class of DAGs, but you need classes that can formalize confounding as well. For instance, acyclic directed mixed graphs, ADMGs, or partial ancestral graphs. Okay, I don't want to go to the details there. We also defined interventional compatibility, and they are not the same. Its difference is subtle. G1 and to Gk are interventionally compatible with respect to the joint distribution. So this also involves a joint distribution. If there's a joint causal DAG having the small DAGs as marginalizations, and there's a joint distribution Markovian to the joint DAG with the corresponding marginal distributions PS, and all interventional probabilities identifiable in Gj coincide with those computed in Gv. So just in a nutshell, that the DAGs coincide with respect to prediction, the graphs coincide with respect to predictions of interventional probabilities. Okay, then we can revisit node ordering algorithm. So if the output of my causal discovery algorithm infers unconfounded edges, then all the outputs are incompatible in the sense I just described. But there's also the useless output. If A always draws confounded edges between the nodes, then the outputs are graphically and interventionally compatible because the algorithm just don't commit to anything. And of course, this is a common pattern. Whenever they don't commit, then they don't contradict themselves for obvious reasons. So to quantify interventional incompatibility, we just computed the pairs for which the interventional probabilities differ across different adjustments divided by the set of all pairs for which interventional probabilities are identifiable. And there's a statistical test that for linear relations that we adapted from Su and Henkel. I don't think that this is the final word about how to define it, how to quantify it. But yeah, it's a bit too strict. I mean, if you have a graph that admits 20 different ways of vector adjustments, and you demand that all of the formulas really coincide, that's a bit too much. So if most of them coincide, this is already a lot if you really work with real data. And even on simulated data, you see all sorts of finite sample effects. Okay, and to quantify graphical incompatibility, we just count the structural Hamming distance between the marginalization of the graph to the subsets and the output on the subsets. We have the following experiments reported in our paper with the causal discovery algorithms RCD and FCI. So here we had to use algorithms that can detect confounding. So this is the linear non-Gaussian model with confounding, the model I just described for the merging example, and this is fast causal inference with conditional independencies, which detects confounders. And here we have shown that the incompatibility score, this is supposed to be incompatibility score, correlates with structural Hamming distance for simulated data. So for simulated data, we know the true graph, and we just showed that the incompatibility clearly correlates with the error, the structural error in both cases. Also have some experiments with real data, the famous data from Sachs and ultra causal protein signaling network. Here's the ground truth graph, and here you get the output of FCI, and I took that output because it nicely shows the following problem, that often FCI doesn't commit. So here these are undirected edges. We end up with some clusters and undirected edges. And here, for instance, all of them are connected. They form a clique. And of course, there's a little contradiction because they agree in terms of the clusters, and in terms of directions, they don't commit. So there's no disagreement, although the result is not very useful. So sometimes algorithms don't commit enough to result in contradictions. This shows, so to speak, the shy version of causal discovery. You draw an arrow and confounder everywhere. You will never be wrong, because according to the chaos theory from the 70s, large effects can result from tiny causes. So that was the famous quote that the flap of a butterfly can cause a tornado in Texas. There is no error that can really exclude it. However, a useful DAG will always be wrong, but we should check how well it describes different environments, extreme conditions, or merging distributions. This refers to invariant prediction by Peters and collaborators. So the future goal would be to define good quantitative performance metrics for these tasks and do honest benchmarking of causal discovery with real data. So I really want to emphasize real data. I don't believe in simulations. And we shouldn't overfit on single performance criteria. And I want to conclude with a sort of vision that doesn't only refer to DAGs and the causal discovery business. So regarding causal DAGs, the visions, because sometimes we do need DAGs with many nodes, we should never forget describing falsifiable implications, and we should be concerned if there are none. And regarding causal explanations in politics, psychology, medicine, or whatsoever, we should always think about potential facts that would make us revise our explanation. And I think this is what is often missing. Okay, this is how I want to conclude. Thanks for your attention. Questions?
Thank you. This was great. I learned a lot. This is not exactly about your presentation. It's about the motivation for it. Can we go back to Guido's quote? I want to talk about Guido's quote.
Oh,
yes.
I was expecting that you want to comment on that.
So I'm a big fan of Guido, and I do some graph stuff and I do some non-graph stuff. But I didn't understand what that was saying at all. Or why we should pay attention to it. It was basically said, I mean, from what I remember, the quote was like, well, it doesn't resonate with economists. Okay. I mean, maybe it should resonate with economists. You know what I mean? Like, I think the sociology here is people in econometrics, they learn some stuff in their econometrics class, like diff and IV and things like that. And because that's what they learn, that's what they use in practice. And similarly with biostats people learn propensity score matching and adjustment, and that's what they do in practice. And, you know, but Wittgenstein said that what the language you know, then is what you can do, what you can think about. So like, this is basically what this is saying. I've learned some stuff in econometrics class, and therefore DAGs are not for me. Like, why should we pay attention to an argument like this?
Did you read the paper?
Yeah, I've read the paper. I mean, in fact, okay. I had some comments for him about.
Yeah, but
anyways,
I mean, he basically claims that, for instance, front door criterion. He says that although it sounds interesting, he doesn't know any convincing example where one should use the front door criterion, because all the examples discussed in the literature are lacking a convincing statement about the ground truth.
Dominik, did you know that the SCR conference, which is the premier epidemiologic conference this year, the paper that won the best paper award was an application of front door?
Okay, no, I didn't know.
I bet Guido didn't know either. It's interesting, right?
Yeah.
Maybe they should read more widely then.
Okay, that's a good point. I mean,
anyways, that's my only comment. It's a great talk, but I don't think this criticism. I mean, I don't understand what not resonates with economists mean as a criticism.
I mean, it's true that, I mean, this is definitely something that I can report from my own work. That interventions are really terribly ill-defined. I show you an example. The cloud computing. Okay, so here are these dependent services. And our variables are the latencies of the microservices. So what is an intervention on the latency? I mean, it's not the problem that we couldn't intervene on it. I mean, all this is owned by Amazon. And if somebody tells us this is an intervention on the latency, we could probably do it, but I don't know what it means. I mean, what does it mean for the computation process if you set the latency of one service to 0? Even though it has to wait for the result of another one. I mean, do you have to tell the result to that microservice in order to have latency 0, or what does it mean? So you can spend maybe 2 PhD theses with constructing interventions for these variables, but this is really the difficulty, and this is a point where I definitely align with criticism of the paper. I don't want to comment on front-door adjustments.
I had a question, and it's very, very nice talk. So in terms of what you were saying, in multi-environment, referencing Jonas Peter's work, don't you find that even more strong assumptions? I mean, he assumes that all the uh, basically exogenous noises have the same variance. To me, that's even more crazy and untestable than the DAG assumptions.
I think you should distinguish between crazy and untestable.
Yeah.
Maybe it is, I think often it is testable and you can just test it.
I'm
Um,
not sure.
I mean, I have examples where I can test it and yeah, it often seems reasonable.
Okay.
So I've seen examples where it was.
Okay. Yeah, maybe it's some, I don't know how you test it because you can again construct many different models that are compatible with this version or another. I mean, at least in something like a linear sum or things, you can make many examples that you could just change the noise variances and still they're compatible, even in a simple confounding with three variables.
Not sure I got that one.
Yeah.
You change the noise.
I mean, if you have some confounder, you can just share. I can show you some simple examples. To me, it's not.
But wait, if you have a causal set, then you adjust for all the confounding, right?
So, I mean, you're not measuring the confounder. Let's say you have a simple, just common cause. And then you even have, let's say, an instrument. Even in that.
As I remember, you have to block confounding paths.
What do you mean you have to block confound? I mean, he just has a test, right? That has different environments where the noise.
Yeah, but then the predictor is not invariant because of the confounding. And your set of variables is not causal in the sense that it doesn't block the confounding.
Yeah, it could be. I mean, we could
Yeah.
discuss it further, but I mean,
Yeah,
my understanding is that's a much stronger assumption at the very least. Let's say even we disagree on whether you can test it or not. To me, it's even a more strong assumption than what we make about DAGs and their identifiability. You have multiple environment, I mean, like talking about selling it to the economists. I don't think any economist would buy all your exogenous noises in every environment has the same variance.
yes, I mean, of course, those assumptions are just in a different context, in a certain context, and you have to test whether they are valid in your context. So,
Thank you. I
Yeah.
think we disagree about this. But thank you.
yeah. Hmm.
Thanks for the talk. Could not some of these incompatibilities happen because these algorithms work under certain conditions and those conditions might not hold?
Yeah, sure.
For
But the
example,
conditions never hold.
yeah,
Yeah.
so for example, if you assume faithfulness, then you have singleton transitivity for sure.
Yes.
And then you can't have collider in one and non-collider in the other because then one of the edges must be gone by singleton transitivity.
Faithfulness is often violated, sure. But
So-
even you have disagreement also from finite sample effects. For instance, for this RCD, I mean, I've tested it myself with even for 500 data points, 4,000 data points, you have a lot of disagreement, even for the very good case with uniform noise. So a linear model with uniform noise, it's very non-Gaussian. More non-Gaussian than most data you see in practice. And still you need a lot of data points to work, to be consistent across substance.
Yeah, that's true. Do you have any Gaussian case, for example? Because in the Gaussian case, usually a lot of these assumptions hold, right? So do you have any
Yes,
examples
yes,
that
for
are
FCI, we have used Gaussian data.
and you get such
Yeah, yeah.
incompatibilities often?
Yeah, yeah.
Well, that's interesting. Thank you.
You're welcome.
Question from online.
Thank you for your talk. My question is more practical and real world near, let's say. So, I mean, exactly on this slide, when we talk about cloud computing, nowadays, when we consider 1,000 of computing nodes, large infrastructure, it's commonly happen that we have multiple root causes. So what are the ways that you have suggested to also help in that kind of cases? Because that will make things extremely complicated.
Yes.
Thank you.
They are complicated, but we have a general definition of root cause analysis. I'm not saying that this is a method. So it's how to define root cause in the first place was a non-trivial problem when we started, and I think we found a reasonable concept that we are more or less convinced of. But of course, for this large-scale applications, it's hard. Yeah. You're welcome.
Thanks, Dominik.